Imagine a student failing a complex math exam. Is it helpful to simply return the test with a big 0 at the top, or is it better to point out the exact step where their logic broke down? Standard reinforcement learning treats reasoning like a black box, offering credit only for the final answer. This paper, titled InT, Self-Proposed Interventions Enable Credit Assignment in Large Language Model Reasoning, explores how we can fix the broken steps in the middle. The core problem here is how outcome-based reinforcement learning assigns blame. If a model gets the final answer wrong, the algorithm penalizes the entire chain of thought, even if the first 5 steps were perfect. Conversely, if the answer is lucky but the reasoning is flawed, those bad habits are reinforced. On very hard tasks where models almost never succeed, the learning signal collapses entirely because there are no successful examples to learn from. To solve this, the researchers propose intervention training, or InT. While standard approaches wait passively for a correct rollout to appear, InT actively mines failed attempts for value. The method operates on the insight that checking a step is easier than generating a full solution. It identifies the exact moment a line of reasoning goes off track and inserts a surgical correction right at that point. The process works in a 4-step loop. First, the model generates a reasoning trace that fails. Second, using the known reference solution, the model rereads its own work to locate the first error. Third, it generates a single corrective step, an intervention, to fix just that error. Finally, the system fine-tunes on this patch trajectory before running standard reinforcement learning, effectively creating a warmer start for the training process. The results of this patching process are significant. As shown in this chart tracking performance over training iterations, initializing the model with these self-proposed interventions leads to consistently higher success rates compared to baseline methods. On the difficult OmniMath subset, simply conditioning on these interventions during inference raised the estimated success rate from under 0.1% to over 1.5%, a 22-fold increase. Self-proposed interventions demonstrates that models can be their own teachers by learning from failure, not just success. By turning incorrect traces into high-quality training data, this method prevents the zero-advantage collapse, often seen in complex reasoning tasks. To dig deeper into these findings, visit emergentmind.com.